I'm sorry I can't be there in person. My colleague Sebastian Marak is there, and he's happy to discuss this with you. A solar eclipse, it produces a supersonic sunshade that travels across the surface of the Earth, as seen in this Discover image. And our project's going to use the eclipse to test out some new ideas for observing the space environment. In particular, we're interested in the ionosphere, which is made visible by the aurora in this view. The ionosphere affects radio waves passing through it, and so we're going to study this region using those signals, in particular GPS signals. Global Navigation Satellite System is the generic term for a GPS. And rather than the highly capable receivers usually used, we're going to use some very cheap, less capable sensors. Why do we want to do this? Well, you're carrying in your pocket a computer that's more powerful than the most advanced computers in the world 20 years ago. Gary Kasparov lost to a computer that was 1/5 as powerful as your iPhone 7. These devices contain an impressive suite of sensors in them. Most important to us is the GPS sensor. And we're going to use this as a handheld space weather station someday. We're taking the first step here. That'll give us literally billions of measurements the world over. Besides telling you where you are, a GPS system can also tell you the total number of ions between you and the satellite 20,000 kilometers away. And we can construct pictures of the ionosphere if we have these measurements distributed across the ground. And the resolution is limitless. The Japanese consortium that produced the GeoNet network really took the lead on this, as shown in this image here. Geological dynamics are imprinted on the ionosphere. And so here what we're looking at is waves that were launched due to the earthquake, and when they reach the ionosphere, they give us a signal because, again, they affect radio waves transmitted through this region. So the ionosphere becomes a huge seismograph of sorts. And if this is going to advance, yeah, it'll advance on its own in a minute. This is another example from an MIT BU collaborative where we deployed GPS receivers underneath the aurora borealis. And the X's in this image are showing instances where the aurora caused a total loss of the GPS signal. And the reasons for this are still not well understood. We're looking into the physics. Okay, what do we expect in an eclipse then? Well, first and foremost, the eclipse produces a region of cooler temperatures in the atmosphere, mostly concentrated in the troposphere and in the stratosphere, surrounded by a hotter region. And because this shadow moves supersonically, the edges of this region are predicted to launch waves, much like waves launched from a boat moving rapidly through the water. The ionosphere, up there at 100 kilometers, is maintained by extreme ultraviolet radiation. And without this source, we expect the ionosphere to partially disappear. In addition to this hole, we might see instabilities develop on the edges of this density gradient. And we may also see evidence for these tropospheric waves moving through the ionosphere just as they did in that earthquake example. So the next thing we want to do then is ask, how do we observe all this? Well, if we put a tight network of GPS receivers down below all this, as just popped up here, we might be able to see these effects in the signals, in the differences between signals that we receive across such a network. And that's really the goal of this work. We know right where the edges of the eclipse should be, and that's where we're going to put our sensors. Here's an example of what was found using this Japanese receiver array. In this case, the dark regions reveal expected waves traveling away from the bow and the stern of the eclipse. So the eventual vision here is to create a massive crowdsourced space weather observatory that leverages GPS signals from the world's 4 billion or so smartphone users. There are many practical hurdles to doing this, including issues like privacy and so forth, but we're going to just sort of take a first step here. The smartphone functionality we're going to simulate using little GPS receivers about the size of a stick of gum attached to a miniature computer, in this case a Raspberry Pi. We're going to deploy these baby receivers next to highly capable receivers in some instances so that we can get a comparison and calibrate this new technology. And then we're also going to deploy these little receivers in separate locations. And where are we doing this? Well, we're doing this in beautiful Missouri because the Missouri Department of Transportation has an incredibly uniform network of existing GPS receivers that we can leverage in this work. So what do we hope to accomplish in summary? We want to demonstrate the use of inexpensive GPS receiver technology to study space weather. And we also want to demonstrate the efficacy of assimilating a small number of high-quality measurements with a large number of crappy measurements, which is a very interesting signal processing problem. And so what do we hope to find? Well, we hope to find the expected eclipse effects in our data, and perhaps we'll also discover some new unexpected effects. Thank you very much.
Thank you, Josh. Wow, that was really good considering you were remote. Do we have any questions in the room for Josh? He can hear you. Come up to the mic, please, if everyone has one. None? Losers. All right. Does that mean that I have to come up with one? So you talk about unexpected things, Josh. They can be truly unexpected things. There must be something that you can think of that may or may not happen when the ionosphere disappears.
Well, we put in one of my schematic slides, I put the sort of speculation that a density gradient coupled with things like pre-existing electric fields in the ionosphere might destabilize the plasma. And that's really easy to see in a GPS signal. We call that scintillation, rapid fluctuations in the phase of the signal. That would be very exciting to find such a thing. We have people that can do plasma simulations to try and understand how such things happen. So that would be one exciting thing to observe.
Cool. Thanks very much. And thank you, Josh. Again, quick round of applause for Josh for participating remotely.